Welcome to a special edition of Physical Chemistry After Dark. In all seriousness, I got my Glenlivet. Well, we're going to talk about some kinetic chemistry. Something that hopefully you know a little bit about. Hopefully you're not coming into physical chemistry without having at least had some kinetics in your general chemistry experience. But we're going to hit this and hit it hard. You'll see why all this calculus is important. Let's get started. So, I just want to reiterate, you should have seen this in general chemistry too. But we'll go a bit more in depth with the math. We'll actually determine some of the mechanisms and see a lot more unusual experiments than just first order and second order. And how will we treat them? But first, let's define kinetics. Say you stumbled into this video by accident. Chemical kinetics is the study of reaction rates and the mechanisms which occur in chemical reactions. It's important because while thermodynamics, it will tell us should a reaction occur, how much energy will that reaction produce. It has no concept of how long would the reaction take to form. So that's where the reaction rates will come in. Reaction rates will look at how concentration will vary with time. Now, take a generic reaction where the element A with a coefficient of alpha and element B with a coefficient of beta are being converted into element C with and D with their respective coefficients. The number of moles of each given species at any time can be defined as so. The number of moles N at a given time I is going to be equal to the sum, or is going to be our initial concentration of N of I at time 0 plus nu, which is our coefficient, respective coefficient for I, and xi. Now xi is a new letter. It's the weird squiggly E, kind of looks like a Z, depending on how you look at it. Xi is essentially the extent of our reaction, how far the reaction has gone. We've kind of seen this before, where if zero reaction is gone, xi would be 0. If we've gone 100%, xi would be 1. So essentially we're saying we're adding our initial concentration plus how many reaction turnovers have we seen. So if we're looking at C at time 0, N sub 0 is probably 0, and we're just going to have, so that's going to be 0. But after so many passes, so many turnovers, is going to be 1 or 2 or 3. That'll be 3 times C, and we'll figure out then how many moles. Now keep in mind, this takes into account the sign, so that if we're looking at concentration of A as a reactant with a coefficient of alpha, so the nu for A is going to be negative A. So we're going to be subtracting xi from our initial concentration. So we'll see that A is going down as time goes forward. Things like D will be going up as time goes forward. So that nu will take care of that, positive or negative. Now, that's all well and good, but we're going to look at how the concentration changes with a fraction of time. So we're going to take the d over dt to both sides. So d over dt gives us dn sub I over dt and d epsilon over dt. So saying that the reaction rate is defined as essentially d xi over dt. That is our definition of rate. How far the reaction has progressed over time. We could also look at the rate as the change in moles over change in time divided by our coefficient. Both of them are equal ways of looking at and defining our rate. So, but the best one is probably look at d xi t time. So reaction progress, the change in reaction progress as time changes. The overall reaction rate will be the same based on this, so we can compare the rate of all converted species. So regardless of whether we're looking at A, B, C, or D, reaction progress will not have changed. If we're still 50% done after 30 seconds, we'll see the change in 50 over the change in 30 seconds. But each of these guys, if I look at the change in A versus change in B versus change in C, those moles may be different, which is why we need this coefficient taken into care, where we can write a generic rate being negative 1 over A dn moles of A over dt equals negative 1 over B d moles of B dt equals 1 over C d moles of C dt, and so on. You may have seen this in general chemistry. It's a way to look at and compare the generic rate to a changing concentration. This will make this extensive rate intensive property by dividing by the rate by the volume, such as R is the rate divided by the volume. R is an intensive reaction rate. Now, look at some rate laws here. A reaction rate depends on a variety of different factors. It depends on temperature. What doesn't? Pressure. So does delta G and a whole lot of other constants. Concentration is going to be a big controlling factor, and even the physical phase or phases present in the reaction. So whether we have all solids, solids and liquids, essentially how well can they mix? A majority of our homogeneous reactions, the rate law can be determined, where we have an empirical relationship between the concentrations and our rate. So we can say that for a reaction R is rate R is equal to a constant K, that's concentration of A raised to a coefficient, concentration B raised to a coefficient, so alpha and beta. For a generic reaction, A plus B goes to C and D. Now, alpha and beta are reaction orders with respect to individual species, and K is our rate constant. So a few things we must note here. K is independent of concentration, but not for pressure or temperature. So if I change the pressure of a reaction, K will change. If I change the temperature of a reaction, K will change. The units of K are determined by the overall reaction order. Basically, rate needs to always, that capital R rate must always equal molarity per second, because we've taken our moles, N, divided by volume, and it's changing moles over volume over time. So we're always going to have molarity per time. It's our reaction rate. So K must always cancel out all the other units present in this rate law here, rate K, A, B, so that we end up with molarity per second. We must always keep these units. So reaction order may be integers, they may be 0, and they may be fractional. But the most important thing is they do have no direct relation to the stoichiometric coefficients. It must always be determined experimentally. It may coincidentally be the same. Alpha may be the same as lowercase a. Beta may be the same as lowercase b, but they do not have to be. They do not have to be. And so that kind of ends up a problem. You have to always check this. So for that reason, rate laws must always be determined experimentally with regards to each reactant. Okay. Now, when we actually measure these reaction rates, say we have a first order reaction where it's simply A goes to B directly, where the rate of where A goes to B does not pass go, and the rate, our capital R, is equal to negative change in A over change in T, thus making our rate law R equals K times A. Now I'm going to generically just say K is equal to 40 inverse seconds. Just a constant, just so we can look at this graph. So if we look at this graph, we see that the concentration of B initially starts shooting up and just starts leveling off. It gets to a point where it reaches asymptotic, where it's almost gone. So a rate will be a rate at any given time will be a tangent to that curve. As we progress, we get different tangents to that curve. We got one tangent at initial rate, and then another tangent at a different rate, where the slope of that tangent will have changed. One thing is readily clear is that the slope will change as time passes. So how should we actually describe this reaction when we look at this? So more often than not, when we look and describe these reactions, we only really want to find out the initial rate, that highest, steepest tangent from the time infinitesimal second that this reaction has started. We're going to have that essentially tangent almost at time zero, in which our exact concentrations can be known. We have it at the starting gate. We know our starting position with absolute certainty, and then we wave the flag, turn on like the green light comes up, off to the races. So from there, if we know our rate constant and the reaction order is known, we can determine the rate at any given time. Partway through the reaction, it's a lot harder to know the actual concentration and do a lot of the measuring, because we don't always know the extent of the reaction. So it's a little bit harder to do. So how will we actually determine the rate or reaction order? Well, in chemistry, we're going to look at this generic reaction. A plus B goes to C, constant K, giving us our rate law of R is equal to K A alpha B beta. So how do we actually determine alpha and beta? The two most common methods are isolation method and initial method of initial rates. The isolation method is when we take one reaction and use it in large excess compared to the other. So really, if I have 10 times, 100 times the concentration of A as of B, one of these guys will essentially change while the other will not change enough to have any initial change. If the change will be like a rounding error for one of these guys. So for example, if I hold A in excess, then the rate essentially simplifies to rate equals constant K prime. Well, K prime is now K times A alpha, because A alpha is essentially doing no change. We can absorb them together and hold it essentially constant, a rounding error. So we can look at how the rate changes just in regards to beta. How is that rate changing? And we can look as time progresses, is it speeding up or slowing down, by what factor? Now, once we find out beta, we can repeat the process, now holding B in excess, and solve for alpha. So that is one way it is actually done in labs. The other way is by a method of initial rates, where we try to perform several different reactions where we vary the concentrations of A and B, where we keep one of these constant between two reactions. We only want to be measuring one variable at a time. And we're going to try our best to measure the initial rate of these various reactions. This is how we did it in general chemistry. So by using the rate of these two reactions, we can solve one another. So if I have rate 1 over rate 2, and say look at the K1 over K2, K's are going to be the same, these will cancel out. A1 over A2 and B1 over B2. Well, if I hold B constant, those B's will cancel out. And so we can encapsulate the A1 over A2 together because they're raised to the same exponent. You can factor the exponent outside of the parentheses. So we can look at how rate 1 and rate 2 change with A1 and A2 factored to the exponent alpha. From there, by taking the natural log to both sides, we'll get alpha out front, and we can look at the ratio of R1 over R2 versus A1 over A2. Once you have that, you can determine the rate law of B just the same. So let's look at this. Let's determine the rate law of this. So we look here between reaction 1 and reaction 1, 2, 3. Between reaction 1 and reaction 2, we see a change here. Between reaction 1 and reaction 3, we see a change here. So if I compare the rate 1 over rate 2 first, A's rate 1 over rate 2, we'll find out our alpha. So we have we'll do rate 2 over rate 1. So 3.31 times 10 to the negative 5th equals 8.26 times 10 to the negative 6th equals 5 times 10 to the negative 2nd, 2.5 times 10 to the negative 2nd. Okay, 3.31 divided by 8.26. That right there, since 3.31 times 10 to the negative 5th, that looks like it's probably 4. Let's see. 3.1. That is close enough to 4.007. This is 2. 2 raised to the alpha equals 4. I don't have to do the natural log to figure this out. The natural log of this would just make it a little bit harder. So alpha equals 2. Okay. Alpha equals 2. So let's look at equation 1 and equation 3. Well, this is 2.48 times 10 to the negative 5th. This is 7.5 10 to the negative 2nd. 2.5 times 10 to the negative 2nd. raised to the power of beta. This is going to give us 3 beta. And I'm guessing that is going to give us essentially 3. 4.8 divided by 8.26. It's close enough to 3. It's 3.002. Okay. So 3 equals 3 beta only if beta equals 1. Now, what I haven't showed you now, how do I calculate K? Well, if I've calculated everything right so far, I can say that R, let's see, no, I don't want that. I can simply say that R sub I divided by A sub I alpha B sub I beta equals K. Why do I say I? Because I'm saying I can look at rate 1, I can look at rate 2, I can look at rate 3. They will give me the same identical K. It does not matter. Does not matter. So I'm going to go ahead and we'll go with rate 2. So 3.31 times 10 to the negative 5th molarity per second times 5 times 10 to the negative second molarity squared and I ran out of room like an asshole. 2.5 times 10 to the negative second molarity. So molarity cancels molarity. So we have 3.3. 10 to the negative 5th. And divided by 0.025 divided by 0.05. And I get K would be, K is going to be our 0.5296 over m squared s. The units of K are going to match and counter the units of our A and our B, leaving only molarity and seconds remaining when we calculate R. So that gives us our final rate law. There I show you down there working it out with experiment 1. And instead of getting 0.5296, I got 0.530, which pretty much is what 0.5296 rounds up to. And so there's how we determine our rate law. Now, well, how do we actually determine these reaction rates? Well, how do we actually measure these initial rates? I mean, it's all well and good to have the numbers, but how do we actually measure the rates as they're being determined? And we have 2 major methods, both chemical and physical, but they really can be described whether ex situ or in situ. Chemical methods typically require the removal of a sample at distinct time intervals, while by immediately quenching this. Either we drastically chill it, drastically heat it up, or do a side reaction that's going to immediately use up one of the reactants. Say like putting it under basic conditions if acid is a reactant, such that it ceases reaction at that time. So you would take a little dropper, suck it up, dump it into a pre-prepared thing, like an ice bath, or shoot it into a base bath. Either way, it quenches the reaction. These samples can then be analyzed a variety of different methods to determine the concentration of one of the desired species. And if you know one of the desired species, you know them all based on that rate dependence that we looked at on like the second or third slide. So we can use it like gas phase chromatography to measure the species. We can use atomic absorption spectroscopy to measure an exact species. Not insane clown posse, but inductively coupled plasma. You can use UV vis. You can even use NMR to determine like a key peak in there. You might have to add a standard to compare. You might have to calibrate it to compare, but you'll be able to measure this as a change in time. This would be considered the ex situ. Now, physical methods will analyze reaction going by measuring physical characteristics such as light absorption, infrared like absorption, or even Raman or NMR. So how are these magnetically active, how polarizable they are. These methods require a little more technical software, but can be more accurate for quick reasons. In any case, we can determine concentration at a time, then we can get a rate. And if we have enough rates, we can extrapolate this back to the initial rate. So in situ would be more like have someone that's recording as the reaction progresses. So it's allowed to react in the reaction cell. So you can measure it without needing to quench it. But that usually requires you to like have microscopic quantities, not nearly large reaction like synthetic scales that you might want to look at. So we'll end on this slide for now. Now, reaction mechanisms will be a large part of the chapter as we're going to look at a bit. So the reason we want a reaction mechanism is because, as I said, our stoichiometric coefficients will not relate to the order. That is, the balanced reaction will not tell us anything about how this occurs. I mean, yes, it tells us reagent A and reagent B are going to be involved somehow, but it could be leaving out reagent C. It could be leaving out a catalyst. It doesn't tell us what's actually going other than we can measure what bonds are being broken in the long run. What is the net change? The overall equation will tell us the net change. But a reaction mechanism is a collection of elementary kinetic steps that involves the transformation of reactants to products. So can we break down the overall mechanism, the overall reaction into a bunch of smaller steps that shows how A goes to B, B goes to C, C goes to D? If I said I'm going to drive to Washington, D.C. right now, and I just left it at that, you don't know how I got there. You might be able to figure out where I'm at. but you don't know the path I'm going to take. A mechanism is going to tell you the path I'm going to take. Am I going to head down through Nashville first and then go on east on I-70 and then turn off at Knoxville? What am I going to do? What am I going to do? That's what the mechanism will tell us. Break this down into individual, easier to follow steps. When I talk about an elementary reaction step, it is a chemical process that occurs in a single step that cannot be simplified any further. At this point, the molecularity or stoichiometric coefficients given in an elementary step will always equal the respective reaction orders for the rate law that's described. We'll leave with this example. For a balanced chemical reaction, NO2 plus CO goes to CO2 and NO. This seems like it could be pretty simple. A molecule of CO bumps into a NO2. It takes off the oxygen, and bada boom, bada bing, there we are. Hey, seems easy. But an elementary reaction maybe what, but the actual reaction may actually involve two molecules of NO2 bumping into each other to form an NO3 and an NO. And then the NO3, being much more reactive, bumps into the CO and then donates the oxygen. That first step may actually be reversible, and that's going to further complicate things. So we can't always tell it by the balanced chemical reaction. Now this guy, NO plus O3 goes to NO2. If this is elementary, one molecule here and one molecule there means this is first order with nitrogen monoxide and first order with ozone. And we know that because it's elementary. And this is why this chemistry is so aggravating. General rule of thumb is you can never know with absolute certainty whether a reaction is right. All you can know is that if a reaction is wrong, we can only eliminate incorrect mechanisms. But you can't ever really prove one is correct. We can just highly suspect it's correct. All evidence points to this. It is yet to be disproven. That's where we're going to stop for now. If this is informative, if it's interesting, please like, please subscribe, please participate. Love to hear from you. This is Chemistry Cowboy signing out.